Hello. In the previous session, we have defined the quantity known as canonical or conjugate momentum or generalized momentum, and we have seen that the generalized momentum corresponding to the generalized coordinate qj is denoted by pj and is defined as dou L by dou qj dot. Dou L by dou qj dot. So this gives you the definition of canonical momentum conjugate to the coordinate, generalized coordinate qj, means corresponding to every generalized coordinate qj for the particle or for the system, we can define an associated or a corresponding momentum which is denoted as what? Pj. And the Pj is related to the Lagrangian of that particular system by the relation that we have seen. So let me call this relation as equation number 1. This is the defining equation for canonical or conjugate momentum in classical mechanics. Okay, and I told you this canonical momentum is a quantity that behaves like the linear momentum in the case of translational motion and angular momentum in the case of rotational motion. So that was the motivation with which this quantity was defined. So Pj is equal to dou L by dou Qj dot becomes the defining equation for canonical momentum. And the linear motion and the linear motion where linear momentum plays the role and the rotational motion where the angular momentum plays the role are two special cases, or specific, can be understood as two specific or special cases of canonical momentum. And I told you why the word canonical is being used. The word canonical has got meaning as divine or by rule, as per rule. Okay, so canonical. So there are several understanding regarding the origin of the word canonical. So canonical actually, see, it's derived from the Latin word canon. Canon, C-A-N-O-N. Canon means law. Canon. So canonical means as per law. Canonical means as per law. So നിയമപ്രകാരമുള്ള എന്നുള്ള ഒരു അർത്ഥത്തിലും നമുക്കിതിനെ കാണാം. നിയമവിധേയമായ എന്നുള്ള അർത്ഥത്തിലൊക്കെ canonical. Okay, so most of you know about, okay, there are mentioning of canonical, the term in many religious text and all. So this is by law, permitted by law, that we also can understand. Okay, so I told you that corresponding to every coordinate qj of the system, you can find out a momentum pj. So we say that these two things, qj and pj, forms what is known as a canonical pair of coordinates and momenta. So they are known as canonical pair. Canonical pair. So I think I explained about why they are known as canonical pair, because now these are the two terms that will always combine together in special contexts such as the Heisenberg's uncertainty principle and all. Okay, so they have got some unexplained, okay, or some sort of relationship, so that they always get combined. Okay, so that is a canonical pair. So the pair of coordinate and momenta which are permitted. Okay, that is why. So it's always the linear momentum paired up with the position coordinate, and the angular momentum will be pairing up with the angular coordinate. Okay, the same manner we have seen that energy, okay, as a variable, energy it be always pairing up with time. So they are all conjugate pairs in quantum mechanics, when you know the foundations are there in classical mechanics. Okay, so that is the thing. So always remember about the defining equation of the canonical momentum. It is given by equation number 1. Okay, so now from this canonical momentum, I will just use this relationship in the Lagrange's equation of motion, and we will see yet another relationship that is coming out, which will be useful for us later. Okay, so let's substitute equation number 1 or use the definition of canonical momentum in the Lagrange's equation of motion. So let's say we have let's see what is happening. We have the Lagrange's equation of motion. The Lagrange's equation of motion. I'm using some short forms for just simplifying our writing. So what is the Lagrange's equation of motion? That is d by dt of the the derivative, time derivative of dou L by dou Qj dot. Is it not? Dou L by dou Qj dot, d by dt of dou L by dou Qj dot minus dou L by dou Qj, is it not? Minus dou L by dou Qj is equal to 0. That is the way in which usually we express the Lagrange's equation of motion. We write this is my equation number 2 for the time being. Now, can't you substitute equation number 1, which is the defining equation for the canonical momentum, in equation number 2, because you can see this particular quantity dou L by dou Qj dot, which now we have designated, we have renamed as Pj, is actually there in Lagrange's equation of motion. So what will be this equation becoming? That is using equation number 1. So equation number 2 becomes d by dt of time derivative of, that's the meaning, Pj, is it not? Dou L by dou Qj dot is by definition, it is what? The generalized momentum Pj. Okay. So it's actually minus dou L by dou Qj. Let me take it to the other side of the equation, so it will become plus. So it is dou L by dou Qj, dou L by dou Qj, right? Now one more thing, see what is d by dt of Pj by our notation that we are currently following. Can you write it as, it's a time derivative of Pj, right? Okay, so I can write this one as Pj dot, Pj dot. So it is that Pj dot is nothing but the first derivative of Pj, generalized momentum, with respect to what? Time. So Pj dot is equal to dou L by dou Qj. So that is yet another relationship that will be of use to us later. So third one. Okay. So just look at these two expressions, which will be useful for us later. Look at the two expressions here. I'm just boxing it. So this is one expression that you have to keep it in your mind always, because this is the defining equation of generalized momentum, and this is yet another expression which is looking very similar, but just note it, how they are related, how they are different. So how these two, equation 1 and 3, are looking very similar, but there is a notable difference there. Okay, what is that? So you might have seen that here it is Pj. Pj equal to dou L by dou Qj dot. This is with respect to generalized velocity. Okay, the derivative of the Lagrangian, the partial derivative of the Lagrangian with respect to generalized velocity will give you the generalized momentum, whereas we can see Pj dot, it is the time derivative of Pj, first derivative of Pj with respect to time, that is equal to the partial derivative of the same Lagrangian. Means same Lagrangian means Lagrangian of the particular system of about which we are talking about, right, with respect to the generalized coordinate. So here it is Pj equal to dou L by dou Qj dot, whereas Pj dot equal to what? Dou L by dou Qj. Okay, you note the difference. So we will be using these expressions 1 and 3 repeatedly in the coming lectures, so that you will understand better, you will comprehend what's the physical meaning behind these expressions. Okay, so just think of that. If this Pj, right, that is something interesting. If this Pj, Pj is the generalized momentum, right? So in the case of translational motion of simple systems, this Pj can be simply the linear momentum P. That is what we have seen in our previous examples, right? So it can be P. So in the case of rotational motion, simple rotational motion, this Pj turns out to be what? The angular momentum L, right? So if Pj equal to P, you can just think of that. What would be Pj dot? So Pj dot is just like what? dP by dt, right? Is it not? P dot. P dot is nothing but dP by dt. And what is dP by dt in our Newtonian mechanics? That was force, related to force. So we'll just see that how this Pj dot is understood. Just have this some idea there. It's no time for us to conclude that this Pj dot is equal to the force. Okay, because it's all generalized languages that we will see shortly. Okay, so that is two of the relevant equations that we get from the definition of the canonical momentum. Right now, having defined what is canonical or conjugate momentum or generalized momentum, we are now in a state to understand the relevance of these quantities. Okay, for that we define another type of coordinates. Okay, so what is known as cyclic coordinates. So this is yet another related concept in Lagrangian mechanics, cyclic coordinates. So these cyclic coordinates are also known by another name. So they are also known as ignorable coordinates. So there are several names by which this one. Okay, so ignorable coordinates, otherwise known as cyclic coordinates. So let me just take some example. Okay, or let me just define what is a cyclic coordinate. See, let's consider a system. Okay, consider a system of n degrees of freedom. So consider a system of n degree of freedom. Okay, means there are some particles, capital N number of particles, and there are some constraints. You remove the constraint or you neglect the constraints, reduce the constraints, and you get what is known as n degree of freedom. Right now, see. So let's say that the generalized coordinates, let you know that as many number of degrees of freedom, okay, there will be that many number of generalized coordinates usually, okay, for the system. So let the generalized coordinates for the system, the generalized coordinates for the system be q1, q2, q3, etc. So we take an intermediate, any particular one, qk, just okay, it goes like this, and finally it reaches to say that qj, right? Qj, or I can say this is qn, right? You know, it will go up to j equal to n, right? So we take it as qn. That's better. It goes up to qn. That's better, because your j value runs from 1 to n, and k is some special value of, okay, this particular thing, qn. It's okay. Now see, if, okay, and you know that usually you will be forming the Lagrangian of the system, right? Usually, you know, the Lagrangian of the system is in general a function of the qj's and, is it not? It's a function of what? Qj's and what? Qj dot. Qj and Qj dot. Possibly time also, you know that, okay? Where the dependence on Qj comes through the dependence on potential energy, right? Potential, which is a function of Qj, and dependence on Qj dot comes through the dependence of kinetic energy on Qj dot. That is it. So L equal to Qj. Okay, so you know that. So let me say that this is a thing. So it is usually defined as T of Qj dot, you know, okay, minus V of Qj. So the dependence are straightforward. Now where j runs from 1 to n. J runs from 1 to n. Okay. Now suppose that if in the Lagrangian of the system you found out the Lagrangian of the system, and that Lagrangian of the system is expressed in terms of its various generalized coordinates. Okay, so suppose that the Lagrangian of the system, if the Lagrangian of the system, you found out the Lagrangian of the system, and if you see that if the Lagrangian of the system is independent of, this is something we have to be very careful about, is independent means free from, okay, is independent of a particular generalized coordinate. It is independent of a particular generalized coordinate. If the Lagrangian of the particular system is independent of a particular generalized coordinate, say, നമുക്ക് എടുക്കാം തൽക്കാലം QK എന്ന് പറഞ്ഞ ഏതോ ഒരു ജനറലൈസ് കോർഡിനേറ്റ്. ഈ QK എന്ന് പറഞ്ഞാൽ ചിലപ്പോൾ Q4 ആവാം, Q5 ആവാം, Q1 Nama, it can be Qn also. Okay, anything. I'm taking just, okay, if it is independent of a particular generalized coordinate, say Qk. Okay, it means that in the Lagrangian, one particular generalized coordinate is absent, because the Lagrangian is usually a function of Q1, Q2, Q3, etc. up to Qn, right? But when on close observation of the Lagrangian, it is found that one particular generalized coordinate is not present, or it is absent in the particular Lagrangian. Okay, so there is one particular generalized coordinate which is absent. So absence is important. All others are present and one particular generalized coordinate is absent. So you have to find out that particular coordinate which is absent. Okay, so if the Lagrangian of the system is independent of a particular generalized coordinate, say Qk, that is Qk is absent. That is Qk is absent from the Lagrangian. Then this Qk is known as, or Qk is called the cyclic coordinate. Qk is known as a cyclic coordinate of the system. Cyclic coordinate for the system. Okay, so it's quite a simple concept for the time being. What is meant by a cyclic or ignorable coordinate of the system? So if the Lagrangian of the system is independent of a particular generalized coordinate of the system, then that generalized coordinate of the system is known as ignorable or cyclic coordinate of the system. Or we can say that in other words, if the Lagrangian of a system does not explicitly contain, explicitly means എന്താണ് വളരെ കൃത്യമായിട്ട് Qj എന്ന് പറയുന്ന ഒരു കോർഡിനേറ്റ് നമുക്ക് കാണാൻ പറ്റുന്നില്ല, അല്ലെങ്കിൽ Qk എന്ന് പറയുന്ന ഒരു കോർഡിനേറ്റ് നമുക്ക് കാണാൻ പറ്റുന്നില്ല. There is no direct dependence of the Lagrangian of the system on a particular generalized coordinate, then that generalized coordinate is called a cyclic or ignorable coordinate. Okay, or it is a coordinate which is absent from the Lagrangian. It's a coordinate which is what? Absent from the Lagrangian of the system. And this cyclic coordinate has got certain relevance, and that is what is important. That is why we just talk about cyclic coordinates. Let's see what's the relevance of the cyclic coordinate. So for that, let me once again go back to our Lagrange's equation of motion. So I have considered that some coordinate Qk among this Q1, Q2, Q3 up to Qn is absent. So Qk is our cyclic coordinate. Let me take it like that. So what is our general equation? So the Lagrange's equation of motion, is d by dt of, generally, that is d by dt of dou L by dou Qj dot, as we are familiar. Okay, dou L by dou Qj dot minus dou L by dou Qj is equal to 0. That is our Lagrange's equation of motion. Now, where you know that J runs from 1, 2, 3, etc. Okay, some intermediate value K, and it goes to N, where this K can be even 1 or it can be N. It's any general value. Okay. Now, if Qk is a cyclic coordinate, if Qk is a cyclic coordinate, means in the Lagrangian you do not find this Qk, all other coordinates are there. If Qk is the cyclic coordinate, then you know, if Qk is a cyclic coordinate, then what you can write mathematically? You can write mathematically that this Lagrangian L of the system will be independent of Qk. So I can write that dou L by that particular coordinate, dou Qk. See, Qk is a special term. Qk is a particular term, maybe Q5 you say. So if you take dou L by dou Qk, it will be of course equal to 0, no doubt about it, because L is explicitly not depending on Qk. So since Qk is absent from L, automatically the partial derivative of L with respect to that particular Qk will be equal to what? 0. Dou L by dou Qk will be equal to 0. And you know that the Lagrange's equation of motion should be satisfied by every generalized coordinate of the system, right? It's not only one generalized coordinate, every generalized coordinate should be satisfying the Lagrange's equation of motion for a given system. So if you write, okay, therefore let me write, so give some equation numbers, that will be easy. Okay, so let me say that this is my equation number 1, and let me say that this is my equation number 2 for reference. Okay, so what will be the fate of equation number 1? Therefore 4 qj equal to qk. Qj equal to qk means for j equal to k, that particular case. Okay, what will be equation number 1 giving? Equation number 1 will give you d by dt of, right, d by dt of, see, dou L by, sorry, d by dt of dou L by dou q, see, in place of j I am substituting as k, this particular value of the dou qk dot, dou L by dou qk dot minus dou L by, is it not, dou qk, minus dou L by dou qk. So what will be that minus dou L by dou qk? Dou L by dou qk is equal to 0. So I can write this is equal to 0. This is equal to 0. Right? What does it indicate? Once again, see, but you know what is there in the bracket? Dou L by dou qk dot. Can you recall what is that? Dou L by dou qk dot, by our previous discussion, by the definition of canonical momentum, you know, dou L by dou qj dot is equal to pj. So what will be dou L by dou qk dot? So dou L by dou qk dot should be equal to pk. Okay, it means this is the generalized momentum or canonical momentum, generalized or canonical momentum, okay, corresponding to, I can use the word corresponding to, അനുപൂരകമായ എന്നുള്ള അർത്ഥത്തിലാണ് കേട്ടോ, ഒന്നിനോട് യോജിച്ചു പോകുന്ന. Okay, corresponding to, which ones pairs up, corresponding to the coordinate qk, corresponding to qk. corresponding to ന് പകരമാണ് നമ്മൾ ഉപയോഗിക്കുന്ന വാക്കാണ് conjugate to, നിയമപ്രകാരമായി പെയറപ്പ് ചെയ്യപ്പെടാൻ പറ്റുന്നത് എന്നുള്ള അർത്ഥത്തിലാണ് ഇവിടെ corresponding to അഥവാ conjugate to. So what is pk? Pk is the generalized momentum corresponding to qk. That was our belief. Okay, corresponding to every coordinate there is an associated momentum. So corresponding to q1 there will be a conjugate momentum p1. Corresponding to q2 there is a conjugate momentum p2. Okay, corresponding to qj there is a conjugate momentum pj, and so on. That is what we have seen. Okay, so dou L by dou qk dot, by the definition of canonical momentum, is nothing but pk, the conjugate momentum corresponding to the generalized coordinate qk, which was identified as a cyclic coordinate. So what I can write is this relation gives you the d by dt of dou L by dou qk dot. So it is nothing but d by dt of, what is that, pk. Okay, that is equal to 0. Or what does it mean? Once again, d by dt of pk is nothing but pk dot, right? Pk dot equal to 0. Pk dot equal to 0, right? So when pk dot is equal to 0, what does it mean? You know, when the time derivative of a quantity is equal to 0, it means that that particular momentum or that particular quantity pk is a constant of motion, is not? That remains a constant, and that is a very, very important conclusion or consequence of a what is known as an ignorable or a cyclic coordinate. Okay, so let me come to the conclusion here. So you can just go through the discussion once again. So let me come to the conclusion. This is our conclusion. If, so the conclusion is this one, it goes like this: if a generalized coordinate, if any generalized coordinate, okay, if a generalized coordinate, say qj or qk, it doesn't matter whether you call it as qj or qk. I wanted to specify that it's one of the particular value of j, that is why I took k. So if any generalized coordinate qk, I'm taking it as qk, is absent from the Lagrangian. So instead of saying that it is absent from the Lagrangian, so I will just say is cyclic. If any generalized coordinate qk is cyclic, then the corresponding, or I can use conjugate, then the corresponding means a pair. The corresponding canonical momentum, then the corresponding canonical momentum or conjugate momentum, pk, right? Corresponding canonical momentum pk is a constant of motion. Means it will not change with time. And you know that instead of saying that it will be a constant of motion, okay, we usually use the word in physics that is pk is conserved. Is not the way that we use. If anything is a constant of motion, we will say that that quantity is what? Conserved. Okay, it is constant in time. Its time derivative is equal to 0. pk is conserved, right? And you know that in physics we always go behind quantities which are conserved, and physicists like conserved quantities. Okay, that is why you know that in physics we talk about a large number of conservation laws. We always start with the law of conservation of energy, which is a very fundamental law of physics, the first principles of physics. Law of conservation of energy we discuss. Then we discuss about law of conservation of mechanical energy. For a conservative system, we talk about the law of conservation of mechanical energy. We talk about the law of conservation of momentum. We talk about the law of conservation of linear and angular momenta. Okay, so the same way, conservation laws plays a major role in, or it plays a critical role in the analysis of physical systems. So the Lagrangian analysis of a system helps us to identify the quantities which are conserved, and that is one of the advantages of Lagrangian mechanics. And you will see that once you are able to write down the Lagrangian of the given system, and if you are observing the Lagrangian of the system carefully, such that if you come across any generalized coordinate that is absent or missing from that Lagrangian, then you should be happy. Okay? Why you should be happy? Corresponding to every missing coordinate in the Lagrangian of a given system, there will be a momentum which is constant. So that gives you an idea about the law of conservation of momentum. And I will take several examples and will just show you that how the analysis of cyclic coordinates in a given system, in the Lagrangian of the system, leads to identification of the hidden conservation laws. Okay, so let me just directly give you some simple examples right away, and we'll be using the concept of cyclic coordinates in real problems later. Like we'll talk about the law of conservation of angular momentum when we discuss about what is known as the inverse square law of forces. Okay, just like the Kepler's or planetary law of motion, you know the angular momentum is conserved, and you will see that how the Lagrangian method is able to directly predict the conservation of angular momentum much before we go to the details of the problem. Okay, so I'll give you one example right away here. See, just let's go back to our simple example used to define or used to introduce the concept of canonical momentum. So let's consider a free particle. Okay, for a free particle. It's always good that you begin with the simple systems for a free particle, and you know that okay, by free particle we mean its potential energy of the system is equal to 0. Okay, for a free particle, you know the Lagrangian. So what is the Lagrangian? The Lagrangian, we have seen that it's basically t minus v, but we have seen that if it is moving along x-axis, so it is half m v square. V square means x dot square minus 0, because potential is equal to 0 being free particle. Is not v equal to 0, right? That's it. So can't you see that the Lagrangian here L here is a function of x dot only. Is not? It's a function of x dot only. The Lagrangian do not have a dependence on x. Here you can take q is equal to x. The generalized coordinate is Cartesian coordinate x, the position, and you don't have any q dot. Sorry, you don't. So if q equal to x, then q dot is equal to x dot. So you can see that the Lagrangian, even though it is generally defined as a function of q's and q dots, in this particular case, the Lagrangian depends only on q dot. It is independent of the q, right? Is it okay? So I can say that it is that is the Lagrangian here is independent of. These are some simple cases, okay? Independent of x, right? So what does it mean? That is, x is a cyclic coordinate here, or I can say x is cyclic, or x is a cyclic coordinate for the system. So you identified that x is a cyclic coordinate for this free particle. What does it mean? It means that, is not? What's our conclusion? Our conclusion is that if a generalized coordinate qk is cyclic, then the conjugate momentum pk should be a constant motion. What type of motion we are talking about now? We are talking about translational motion. So which is the conjugate momentum or canonical momentum? So the conjugate momentum or generalized momentum, right? The conjugate momentum corresponding to x, corresponding to the cyclic coordinate x, which is that is nothing but the linear momentum px. If you want, you can just write it's px, x component of the linear momentum. Px is a constant. Px is must be a constant. That is our conclusion. That is what the Lagrangian mechanics says. So if x is cyclic in the Lagrangian of the system, then certainly with 100% guarantee you can just confirm that its conjugate momentum must be a constant, or its conjugate momentum must be conserved. And you know from your experience of Newtonian mechanics, it's not a new result at all, because Newton's Newtonian laws actually have predicted this particular concept. Is it not right? Why? Because we have seen that it just says that momentum p is equal to a constant, and under what situation, under what situation Newtonian mechanics predicts that the momentum of a system is a constant? That is your second law, right? Okay, what is that? So F equal to dp by dt. F equal to dp by dt. Okay, and if dp by dt equal to 0, right, then it happens when F equal to 0, right? So when F equal to 0, dp by dt equal to 0. And that is, can you see that? Okay, we have mentioned that the system or the particle is a free particle. And what's the meaning of free particle? We have explained before that a free particle is a particle which is free from all external interactions, which is free from external force. So by the way you say that it's a free particle, we conclude that the force acting on the particle is equal to 0. And Newtonian mechanics says that when the force is equal to 0, its momentum should be conserved. And the same thing, you can see that the same concept can be expressed in terms of the Lagrangian mechanics through the idea of cyclic coordinates. Hope it is clear to you. So you can see that the Lagrangian mechanics is actually confirming the results that is given by Newtonian mechanics. That's why we say that the Lagrangian mechanics or analytical mechanics is not entirely a new branch. It's just a reformulation of the Newtonian mechanics. Lagrangian mechanics is nothing but a reformulation. It's not an entirely new formulation. It's actually a reformulation of Newtonian mechanics. Like that usually we have operating systems. Our computers or your smartphones are based on operating systems. And these operating systems, like you have got Windows, operating system, Windows 95 was there, Windows 97 is there, Windows 2000 is there, Windows, just you have got all, new versions of operating systems. And these operation systems are maybe you can say version 1, version 1.1, version 1.2, like this you say. So what's the meaning? The meaning is that there are certain advanced reformulations. So whatever things you are doing in the new system, it can be compatible with what? The old system. It's not just denying anything that is old. It's just an improvement. So the same manner, always understand that the Lagrangian formulation is an advanced formulation. It's a reformulation of the Newtonian. So it does not violate anything what was told by what the Newtonian mechanics. Right? It has got certain advantages and it has got certain limitations. This is one way to understand. Okay, so I think you are able to understand that the cyclic coordinates, the identification of cyclic coordinates in a given Lagrangian will help us to directly understand the conservation laws which are associated with a particular system. This is one example, and you can just take, I will go for complicated or more involved examples later in when we come to real problems, but you can take always, you can also just think of for a free particle which is rotating. Okay, for a rotating particle, a rotating system, you can see that the Lagrangian, already we have seen that for the Lagrangian, so what will be Lagrangian equal to? It will be equal to simply half I theta dot square, right? Half I omega square. The rotational kinetic energy only will be there, right? So you can see that this Lagrangian is independent of the generalized coordinate theta. So L is a function of theta dot only here. Means theta is the absent generalized coordinate. Theta dot present ആണ്, പക്ഷേ അതിന് generalized coordinate ആയ theta absent ആണ്. നമ്മുടെ ശ്രദ്ധ പോവേണ്ടത് ലഗ്രാഞ്ചിയനിലുള്ള ഏത് കോർഡിനേറ്റ് ആണ് ആബ്സെന്റ് എന്നാണ്. വെലോസിറ്റി ടേം ഉണ്ടാവാം. തീറ്റ ഡോട്ട് ഈസ് വെലോസിറ്റി, ജനറലൈസ് വെലോസിറ്റി. പക്ഷേ ജനറലൈസ് വെലോസിറ്റി തീറ്റ ഡോട്ടിന് കറസ്പോണ്ടിങ് ആയിട്ട് ഉള്ള തീറ്റ എന്ന് പറയുന്ന കോർഡിനേറ്റ് എന്താണ്? നമ്മുടെ ലഗ്രാഞ്ചിയനിൽ ആബ്സെന്റ് ആണ്. അപ്പോൾ ആരാണ് ആബ്സെന്റ് എന്ന് കാണാൻ നിങ്ങൾക്കൊരു കണ്ടുണ്ടാവണം. ഓക്കെ, നമ്മുടെ ശ്രദ്ധ പോവേണ്ടത് ലഗ്രാഞ്ചിയനിൽ ആരാണ് ആബ്സെന്റ്. ഏതൊരു സിസ്റ്റത്തിൻ്റെ ലഗ്രാഞ്ചിയൻ കിട്ടിയാലും അതിനകത്ത് ജനറലൈസ് ക്യൂ ഉണ്ടാവും, ക്യൂ ഡോട്ടും ഉണ്ടാവും. പക്ഷെ ചില ക്യൂ ഡോട്ടുകളുടെ കോൺജുഗേറ്റ് ആയിട്ടുള്ള companion ആയിട്ടുള്ള ക്യൂകൾ മിസ്സിംഗ് ആയിരിക്കും. സോ യു ഷുഡ് be careful about those missing coordinates, and that missing coordinate gives a hint about what the the conservation laws. Okay, so theta is cyclic here. So when theta is cyclic, what you can say? Theta യുടെ conjugate ആയിട്ടുള്ള, so momentum conjugate to theta. See, the momentum conjugate to theta, എനിക്കത് നമുക്കറിയാം അല്ലേ, റൊട്ടേഷൻ മോഷനിലുള്ള ജനറലൈസ്ഡ് മൊമെൻറ്റത്തിന് നമ്മൾ വേണമെങ്കിൽ എന്ത് വിളിക്കാം? ഞാൻ അതിനെ തൽക്കാലം പി തീറ്റ എന്ന് വിളിക്കുകയാണ്. ദിസ് ഇസ് എ ഫേവറൈറ്റ് സിമ്പിൾ. പി തീറ്റ എന്ന് പറഞ്ഞാൽ മൊമെൻറ്റം കോൺജുഗേറ്റ് ടു ജനറലൈസ്ഡ് മൊമെൻറ്റം കറസ്പോണ്ടിങ് ടു ഓർ കോൺജുഗേറ്റ് ടു വാട്ട് ഇസ് നോൺ എസ് വാട്ട് ദ ജനറലൈസ്ഡ് കോർഡിനേറ്റ് തീറ്റ. ഇതിനെയാണ് നമ്മൾ എന്ത് വിളിക്കുന്നത്? ആംഗുലർ മൊമെൻറ്റം എന്ന് വിളിക്കുന്നത് അല്ലേ. റൊട്ടേഷൻ മോഷനുള്ള ജനറലൈസ്ഡ് മൊമെൻറ്റത്തിനെയാണ് നമ്മൾ ഇത് വിളിക്കുന്നത് ആംഗുലർ മൊമെൻറ്റം, എൽ എന്ന് വിളിക്കാം. സ്മോൾ എൽ ഉപയോഗിക്കുന്നു, കാരണം ക്യാപിറ്റലിൽ നമ്മൾ ലഗ്രാഞ്ചിയൻ ഉപയോഗിക്കുന്നതുകൊണ്ടാണ് ഇവിടെ സ്മോൾ എൽ എന്നുള്ളത് അല്ലേ. നിങ്ങൾ ആംഗുലർ മൊമെൻറ്റം ക്വാണ്ടം നമ്പർ ഉപയോഗിക്കാറില്ലേ? the principal quantum number n, then you have got L, angular momentum quantum number L ഉപയോഗിച്ചിട്ടുണ്ട് അല്ലേ. then magnetic quantum number m and spin quantum number. so L എന്ന് പറയുന്ന ആംഗുലർ മൊമെൻറ്റത്തിനെ റെപ്രസെന്റ് ചെയ്യുന്നുണ്ട്. so L is equal to അല്ലേ, so p theta or L is equal to a constant. L is equal to a constant, and you know that this is nothing but a direct consequence of the Newton's second law of motion in rotation motion. എന്താ പറയുന്നത്? if the torque acting on the system is equal to 0, നിങ്ങൾക്കറിയാം ഇവിടെ ഫ്രീ ഫ്രം അല്ലേ, ഫ്രീ സിസ്റ്റം എന്ന് പറയുന്നത് ഇറ്റ് ഇസ് ഫ്രീ ഫ്രം ടോക്ക് ആണ്. എക്സ്റ്റേണൽ ടോക്കിൽ നിന്നും ഫ്രീ ആയ ഒരു സിസ്റ്റമാണ് എന്ത് ചെയ്യുന്നത്? നമ്മൾ ഫ്രീ സിസ്റ്റം എന്ന് റൊട്ടേഷൻ സിസ്റ്റം എന്ന് പറയുന്നത്. ഇഫ് ടോ ഈക്വൽ ടു 0 then dl/dt is equal to 0 എന്നാണ് നമ്മൾ പഠിക്കുന്നത്, റൈറ്റ്? സോ then automatically L should be a constant. Okay, so that is our conclusion. Before I just conclude it, let me wind up by just briefing what we have taken from here. So we have defined what is known as a cyclic coordinate. What is meant by cyclic coordinate? It is any coordinate of the system which is absent in the Lagrangian of the system, or if any coordinate is missing from the Lagrangian of the system, then that coordinate will be cyclic coordinate. Other words, you can say that if the Lagrangian of a given system is not having explicit dependence on any of the coordinate of the system, then that coordinate is known as cyclic coordinate. And the relevance of cyclic coordinate is that if any generalized coordinate is cyclic, then the corresponding canonical momentum will be conserved. So the identification of cyclic coordinates in Lagrangian of a system will help us to conclude about the hidden conservation laws. Okay, we will do more examples in the coming discussions. Thank you.